Okay, anyways, I just brief you guys first because I sent you all the message, right? Okay, about the coming year lah. Okay, because now it's pretty much towards the end of the year already. You're going to go overseas soon. Okay, just to brief you guys again, right? We have planned out the entire syllabus for next year. So we have every single week, right? We have planned out exactly what to do. Okay, all the revision, everything, topics, everything also planned out. Okay, and after we have done the planning already, right? Okay, we realized that we are slightly behind lah because now we haven't enacted the plan yet. Yeah, okay, so no choice lah. Okay, I just reiterate one more time for the sake of the recording also. We are going to cover 2 lessons of solubility equilibrium. Today is the first lesson. This topic can be covered quite quickly, all right? And the other one will be arenes. Okay, for you guys, right, we haven't really managed to cover arenes yet. I'm still in the midst of uploading arenes. I've uploaded 2 lessons already. If you guys want me to print the notes for you, okay, later I can print for you also. Okay, but generally, right, what I need you guys to do is to catch up on arenes yourself. Okay, arenes, solubility, I'll do with you guys. Arenes, if you got anything, right, okay, feel free to see me for consult whenever I'm back in December lah. Okay, I'll update you all more on that. Okay, but anyways, yeah, okay, you all need to study arenes yourself, right, before the next year because I have no time to cover that, right, after we have planned out the entire schedule. Okay, but never mind, we'll be in case next year lah. Once we do this messy thing, we sort this messy thing out for the month. Okay, so let's begin on solubility. I assume that I'm pretty sure you guys have not covered this topic yet. Okay, but I feel that you guys have covered this topic called chemical equilibrium. This is the second part of the equilibrium series, right? We call this solubility, right? There are a few things we're going to do today. Okay, and then this first segment, right, we are focusing more on KSP and solubility, which is a small letter s. We'll come to this later. Okay, but let's look at the first page of the notes, right? We're going to understand the definition of solubility. What does it mean? Okay, if you're going to scan through very briefly, right? Okay, it seems quite normal. Okay, the number of moles of solute they can dissolve in 1 dm cube of water. So imagine this: you have 1 liter of water of a water bottle, right? How much of something can you dissolve inside? That represents the small letter s, solubility. Now, there are a few things that I need you all to highlight. Number 1, the word saturated solution. In fact, that's the only thing I need you guys to highlight. Okay, the word saturated solution is very important. Okay, later I'll come out with some values for you all. Okay, but the most important term here is the word saturated. Guys, any idea what saturated means? Any guesses? If a solution is said to be saturated, what does that actually mean? So if you all take a look, and let's say you always buy coffee by tea, right? Okay, it will taste nicer if the coffee is so-called thicker, right? Okay, we always like to use the word thicker. But in chemistry, we're going to use the word saturated. A saturated solution, in other words, just means the maximum amount of ions that are inside the solution. So, different salts in this topic have different solubilities. Like for example, we all know, right, that NaCl is a very highly soluble salt. So guys, think about it. If a salt like NaCl is very soluble, will there be a lot of ions in the solution or very little? There will be a lot, right? You can see that. Okay, because you have turned all the solid into ions. But I want you all to acknowledge one thing. In secondary school, we learned that there are such things called insoluble salts, right? We're going to throw that term out of the window because there's no such thing as an insoluble salt. In fact, we only know of the word sparingly soluble. So for example, we have AgCl. AgCl is a very, very common example. It can only dissolve to a damn small extent. So if you take a look at this right here, we're going to use equilibrium arrows. That's why this topic is an equilibrium topic. Okay, only a very small amount of solid is going to turn into ions. So guys, will the maximum amount of ions in the solution be very high for this AgCl? No, right? There's going to be just a little bit of ions. That's pretty much what we're going to discuss. Again, we're not going to focus on highly soluble salts, okay, because we need to have an equilibrium reaction. Okay, so that's number 1. Okay, number 2, right? I'm going to introduce some values. So for example, if I were to tell you guys that AgCl has a solubility of 3 moles per dm cube, what does this number actually mean? So if you all notice, right, the units for solubility is the same as concentration. So what exactly is the difference here? So guys, it's very simple. You can only dissolve a maximum of 3 moles of AgCl in 1 liter of water. Does that make sense? So see, can I dissolve 2.9 moles of AgCl in that 1 liter water? Is this possible? If I throw 2.9 moles into that water, can I dissolve all 2.9 moles? Yes or no? Okay, answer should be yes, right? Because the maximum it can dissolve is 3. So if I tell you guys, if I add 3.5 moles, will all 3.5 moles dissolve into ions? No, right? Because only 3 moles will dissolve into ions. Then guys, what about the remaining 0.5? What is it? No matter how hard you stir, it's just solid floating on top. Does that make sense? Okay, so you know this, okay, have a mental picture in your head first. You need to be able to interpret the values. So if I try to throw in 3.5 moles of AgCl, only a maximum of 3 moles have turned into ions. Whereas no matter how hard you stir, you're just gonna get a bunch of shit floating on top over here, right? This is your 0.5 moles of solid AgCl. So that's the idea behind solubility. Every salt has a certain solubility value at a given temperature. So when the temperature changes, guys, you all think about it. When the water is hot, right? Is it easier to dissolve stuff or is it harder to dissolve stuff? Okay, when the water is hot, is it easier to dissolve or harder? Okay, it's definitely easier, right? That's why you all make Milo that time you use hot water first. Okay, that's why, right? Okay, that one we'll look into it a little bit more. Okay, in this topic, okay, of course, we're not going to look at such high values. We're going to look at 10 to the power of negative 5, 6, that kind of scale. Okay, and I want you guys to now write down this equilibrium reaction here, because we have learned ICE table before. And I want you guys, right, to kind of like contextualize this value 3 mole per dm cube in this ICE table. Okay, so let's try this. Number 1, I'm going to add in 10 moles of AgCl. Okay, all this is done in a 1 dm cube solution. Okay, I'll just write it at the side. Okay, all this is done in a 1 dm cube solution. So if I throw in 10 moles, okay, of course your Ag plus Cl minus at the start, what value should be? What's the value of it? It should be 0, right? Because you haven't done anything yet. Nothing has dissolved yet. Okay, I've thrown in 10 moles of AgCl. And I already told you guys that there are only a maximum of 3 moles that dissolve. So guys, what should your change? What's this value here? What's the value of change? Should be what? Okay, should be 3, right? Again, minus 3. Because you're going to dissolve some solid. How much solid can you dissolve? This guy can only dissolve 3 moles. That's the maximum. You can't dissolve 4 moles. Okay, this is just the maximum it can dissolve, right? And guys, what about the values over here? Let's just fill in row by row. What should you put for the change for Ag plus and Cl minus? What should it be? Okay, it should be plus 3, right? Because now you have converted the AgCl solid into ions. And remember, the most important thing over here is still holding up. Your change must follow mole ratio. We learned this in chemical equilibrium, and it's going to be the same, right, for all equilibrium topics. Your change must follow mole ratio. So, if all this is 1:1:1, very simple. Later, we'll look at more example stuff. Okay, and of course, I'm sure you guys can fill in the rest of the table. 10 minus 3 here, I get 7, then this one got 3, this one got 3. Okay, and I want you all to be able to interpret, right, exactly what this means. Okay, and first so far, right. What does your change actually represent? If you all realize, I already gave you all this value here. In other words, your change, yes, it follows mole ratio. Your change represents the solubility of the salt. Remember, solubility is the maximum amount of solid that can dissolve. For AgCl, the maximum of 3 can dissolve. So the solubility is just 3 moles in 1 dm cube of water. Something like this. Okay? Guys, then what does the equilibrium represent? Right now, you all think about it. My big ass solution over here, right, has 3 Ag plus ions, 3 Cl minus ions, and what? What does this 7 represent? Are these ions? No, this 7 over here is just your 7 moles of AgCl solid floating on top of the solution. And in other words, guys, your equilibrium, what does it actually represent? Okay, this represents, okay, after everything has settled down, this represents the saturated solution. Again, because a maximum of 3 can dissolve, right? So that's why you only have a maximum of 3 ions. Does that make sense? Okay, so when the dust has settled, right, you can only have 7 AgCl and 3 of each ion. You can't go to 4 ions, it's impossible because this is the maximum you can dissolve. So this equilibrium here, your 3 and 3 represents a saturated solution with the 7 just floating on top. Any questions so far? So I'm really going in depth. Okay, I don't want to rush through this portion because it's very important for you all to understand the two things. What solubility, what this value represents, and the idea of is saturated. Okay, so far? Any questions? Okay, any questions, just stop me up. Okay, but now, okay, page 2, page 3, okay, I've gone through all this already. Okay, so I want you guys to now turn over to page 4. Okay. So we went over the idea of solubility. Now we're going to take a look at KSP. Okay, so in equilibrium, right, you guys have learned Kc, right? Remember? Okay, Kc, Kp. We're just going to have another one. Okay, we call this KSP. Now, SP stands for solubility product. That's the full name. Okay, the definition doesn't really matter. Okay, but I just need you all to highlight one thing, which is your saturated solution. Okay, so same thing. Solubility and KSP, the reason why I go through both of them together is because of this commonality. They both have a saturated solution. In other words, it measures the maximum amount of ions once again, right? And let's just practice, right, how to write the KSP expression. Okay, if we refer to this one here, this is the sparingly soluble salt. What is the KSP expression? In fact, can you all remember? How do I write the K expressions generally? Is there a rule? Is what divided by what? Can you remember? Okay, some must know what? Okay, when you write a K expression, it's always what divided by what? Okay, so remember this, generally speaking, all the Ks you will learn in your syllabus, it's always products over reactants. All got it? Okay, so we're just going to do the same thing over here. Okay, can you take a look at this equation? AgCl dissociate into the 2 ions. Same thing, I'm just going to look at the products. The products contain these 2 ions, right? Okay, so it's just Ag plus Cl minus. Right? So that's your products. Then what do we do next? We just divide by the reactants. Okay, guys, if you take a look at the notes, you realize that this is the answer already. Why do we not divide by the reactants in this topic? Okay, these ions over here, this is the concentration of ions, right? But why is it that AgCl isn't included in the expression? Any idea? Yes, exactly. It is a solid, and solids do not have what? They do not have concentration. Okay, so take note of that. In this entire topic, right, we are dissociating solids into ions. So in this entire topic, we are just going to have the products. So it's a little bit special, okay, but the rules still follow. It's always products over reactants. Okay, so that's your KSP. Okay, there's a very small question on page 4. Okay, why is it that KSP, right, doesn't apply for fully soluble salts? Not for these dudes over here. KSP only applies for this equation, but not for fully soluble salts. Guys, the clue over here, right, is in the arrow. For fully soluble salts, do we use the reversible arrow? In fact, what arrow do we use for a fully soluble salt? Okay, the full arrow, right? And a full arrow, have we ever used equilibrium constant for a full arrow reaction? No, right? Because there's not even an equilibrium in the first place. So the very simple answer to this is fully soluble salts, okay, will dissociate completely in water, right? Okay, fully dissociate in water. So there's not gonna be any equilibrium in the first place. Okay, no equilibrium is set up. So how do you expect yourself to use an equilibrium constant for a non-equilibrium reaction? You get it, right? Okay, it just doesn't make any sense. Okay, so that is your simple answer. Okay, again, they won't test this, just food for thought. Okay, for you to kind of understand this a bit better. Okay, any questions so far? Now, the one property about KSP that you guys confirm 100% need to know is the same as your KC, KP, K whatever lah. Okay, all the 3 have the same commonality. Okay, it's only affected by what? Can you all remember? Same for KSP as well. The value of Kc and Kp, KSP, is only affected by temperature. Good. Okay, so it's only affected by temperature and it's just unaffected by concentration. So no matter what, no matter how I change the concentration of the ions, I am not gonna change the concentration. Okay, only temperature will change that. Okay, that's just a property, right, of all equilibrium constants. All, there's no exception here. Okay, so that's for bottom of page 4. Okay, if not, right, we're just going to take a look at the next page, and then we're just going to write down some examples of your equilibriums. Okay, so there are plenty of examples there, right? Let's try this out. A few things. Okay, number 1, equation. Number 2, KSP plus number 3, units. Okay, so maybe I'll go through the first one with you guys. Okay, first thing I need y'all to do is to come up with an equation, and this equation, try to write state symbols now for practice. Okay, remember, we are always starting with a sparingly soluble salt. This guy can dissociate into Pb2 plus, and I minus, remember here got 1, 2, okay, to balance this. Okay, and just based off this, right, okay, go and try to write a KSP expression. The units, this one should be also self-explanatory. Okay, give it a try. Okay. Okay, quite repetitive this segment. Okay, just go and keep trying. Right. Just be careful with the last one, because the last one has a lot of numbers. There's actually very units. Yeah, units for KSP. Based on the number of concentration terms, it just going to math it up. Make the first answer on the board. Right. Check your KSP expression first, okay, then your units will follow. You know, Ita came back from Japan, right? He say that Tokyo sucked. He said it was bad. I was like, taken aback. Why is it bad? Then he said the place felt very undeveloped, underdeveloped. So it was like, he said the place felt a bit rabak, a bit poor. When he said the bird poor, then I'm like, bro, you're too rich with you. Then no lah, because he said like, well, people are using like iPhone 10 in the street. I don't understand. That was a city, the capital. Shouldn't it be like the, you know, the best or something? I don't know. Yeah, I don't know what's his deal lah. He's shit up like, bro, no one has complained about Tokyo before except for you. So I don't know how true it is. To go there, find out myself. Yeah, I'm very angry. But I'm more excited for Osaka. I watched this video on YouTube, right? It's like this guy, right? This Japanese guy going around to interview the people in Osaka, right? While they are drunk, so that like it's for the drunkards in the street, right? Wow, they are actually damn wild when they are drunk. They become damn gay and shit, dude. It's damn funny. It's just this guy, right? Just go around and those people saying the most random shit. It's damn funny. Yeah, so I can't wait to see, right, how the drunk people there are actually like. They're gonna be quite funny. Gonna document all that shit over there. Okay, anyways, I'm just gonna quickly review the rest answers. Okay. Okay, for the units, right? Okay, just go and check. Okay, we just need to count all the number of terms correctly. Okay, the last one is just go and again very, very big numbers here. Okay, but calcium 2 plus Q and then the phosphate ion squared. Okay, remember it's always the coefficient that turns into the power. Okay, 3 plus 2 is 5, so use your math. Okay, 4, 5, 10 to the power minus 15. Okay, that's pretty much this long. And so far, right? Okay, generally, this first part of the topic here, I just need you all to understand just a few things. Okay, all these little but very, very technical stuff, right? I don't think you're all gonna struggle with it that much. Okay, so and so far. Sorry, which one? Yes, KSP will never include the solid. Yes, products will always be equals because in this case, we're just trying to dissociate a solid into its ions when you mix it with water. So yes, your products will always be equals in this state. Okay, if there are no issues there, we're just going to move on to page 6. And we're going to finally, right, draw the connection between KSP and solubility. Just now, I just briefly mentioned that they only have this same commonality of saturated solution. But the numbers obviously got different numbers. We need to see how the numbers are like. Okay, so I just need you all to look at this table in your notes. And I want you to compare two salts. Okay, you all look at AgCl and AgBr. Let's do a few comparisons. Number one, who has the higher solubility? AgCl or AgBr? I don't just observe and just tell me. Who has the higher solubility? Okay, good. AgCl has the higher solubility. Now who has the higher KSP? Okay, still AgCl. Okay, so based on this first pair of salts, right? Okay, there is a very nice relationship you can see over here. Does higher solubility mean higher KSP? Of course, sample size a bit too small. We need to check the other comparisons as well. Okay, but can see what we're doing here. Okay, we're just trying to figure out a relationship. Okay, so it could mean that higher solubility means higher KSP. But now I need you to compare between AgCl and the very final salt there called silver bromide. Okay, Ag2ClO4. Okay, again, who has the higher solubility in this case? Who has the higher S? Okay, Ag2ClO4 has the higher solubility. Who has the higher KSP? Okay, what's going on over here? Now AgCl has the higher KSP. So does higher solubility mean higher KSP? Just based on this information is not lah. Okay, but based on the previous information, it is. So what's going on here? Why is it so conflicting? Is there even a relationship at all? Okay, so I need you all to realize the relationship holds when you compare AgCl and AgBr, but it falters, right, when you compare these two salts. Now, there's a reason why I picked out these two salts, and I'm not going to just review the answer here. I need you all to look at exactly the salts that I picked out for you guys and tell me why the relationship holds for the first but it doesn't hold for the second. Any idea? Perhaps, okay, it's kind of like more ratio. I get what you're trying to get at, right? But more specifically, when you write down the KSP, okay, what do you notice? For AgCl, you will just write Ag plus, Cl minus, right? Okay, for the KSP of AgBr, you realize it's the same. It's also Ag plus and Br minus. Okay, and you mentioned the word mole ratio, pretty much that's what's happening over here. Ag2ClO4, if you write the KSP expression, what do you realize? You'll be Ag plus and then there's a square because there's a 2 there, and then there's ClO4 2 minus. In other words, yes, you're not wrong. Okay, we can use the word that they have different mole ratios. But also, at the same time, guys, these two have how many ions in the KSP? They have 2 ions, okay, but to be more specific here, they have 2 concentration terms. Whereas for this one, how many concentration terms do we have? 3. So guys, is it fair to compare something that has 2 concentration terms versus something that has 3? Clearly, no, right? The KSP is just not accurate to compare across different concentration terms. So that means, guys, the relationship only holds if you have the same number of concentration terms. Different is just not fair to compare. Does it make sense? We're going to put this at the back of our head first, later we'll come back to the application. Can? And so far? Okay, again, next up, we're going to perform some calculations. It's a very calculation heavy topic. So I need you all to look at page 7. Okay, on page 7, let me just show you guys some calculations. Right, okay, so we'll read through the question first, okay, and I will guide you through this before you all try the next question. Right? Okay, so we have already established a relationship. Solubility and KSP are linked together. And now, what we're going to do is to perform calculations related to both. So when it comes to calculations, first of all, okay, I always need you guys to write an equation. Okay, when it comes to all equilibrium topics, I will be revisiting this idea. You must always write out an equation first. Okay, so let's do that. For this case, I have Ag2SO4, right? Ag2SO4 dissociates into, okay, you can write down the equation yourself as well. Okay, these 2 ions, right? Now, we're going to build off this equation. The second thing we're going to do, okay, is to define solubility. Okay, now, this seems a little bit redundant when I do it now, okay, but at the end of the day, you will see why. Okay, the S, this is S for solubility. Okay, so I want you to write this down. Let S be the solubility of Ag2SO4. Okay, this question wants us to find KSP. So our final step is once we figure out solubility, we can substitute solubility into KSP's expression and we eventually get the answer. Okay, but you see now I tell you all the steps, right? It doesn't really make any sense. Okay, come we take a look at the steps itself. Okay. Okay. I can tell you guys that in this topic, we don't actually need to write down this IC table for good reason. Okay, because I want you guys to ask yourself, we are only focused on solubility. Guys, based on solubility, like what we saw just now earlier, which row am I concerned with? Solubility, which row am I concerned with? I, C, or E? If I want to find S, solubility. Remember, I wrote something here just now, but you erased already. Okay, C, yes, because your solubility is your change. And change follows what? Why is this 3 and 3 and 3? Because your solubility, your change must follow your what? Mole ratio, exactly. So that's why in this topic here, we don't actually need to write an IC table. So if you just look at me for this, if the letter S is the solubility of the salt, like what we saw just now, S in this case is 3. So that means the solid in this case, right, okay, has a solubility of S, right? What would be the ions then? What will be this Ag plus? 2S, and then this will be S. Now guys, why is it that why am I only focused on change? Am I not focused on equilibrium? Because equilibrium values, then you can start into the equilibrium constant, right? But do you notice the change and the equilibrium is the same thing? Because your ions started off as 0. You can see that. So that's why this change, these values here represent the change. But for the ions, it also represents the maximum amount of ions that's inside the solution. Can see that? Yeah, the same value. So that's why we can immediately take these values here and perform our calculations. Okay with that? Yeah. So what I'm going to do now is this. Once I've defined all this, I can substitute my S into my KSP. So first of all, I want you guys to go and write down the KSP expression. Give it a try first. And once you've written down the expression, right, I need you all to start to substitute these values into the expression. Okay, give it a try. Okay, just do that first. Okay, then we will continue. Okay, expression first. Right. Okay, so this one shouldn't be struggling with this. Okay, AG plus square SO4 2 minus. Okay, now what do we sub the values into here? What's this? AG plus. AG plus, the final equilibrium concentration is 2S, right? So this will be just 2S, whole thing square, and SO4 2 minus is just S. So guys, what's the full thing? 4S cube. Now guys, take note, a lot of people write 2S cube. But that's wrong, okay, because you need to bracket the 2 also. This is not just math. You just be careful with that. Okay, so 4S cube is your value of KSP. Now take a look at the next thing. They want us to find KSP. We need to find 4S cube. And from that, we need to find the solubility of the salt. Have they given me the solubility of this salt? They have to, right? Okay, and they have. Okay, so you can see there, the value of solubility is actually 4.47 grams per dm cube. But guys, you can just pretty much have this in mind. They will never ask for gram per dm cube. It's always in mole per dm cube. So guys, how do you convert this into mole per dm cube? What should we do? How do we convert gram per dm cube into mole per dm cube? Do you notice, am I doing anything to the dm cube? No, right? I'm simply converting grams to moles. What's the connection here? You divide by the MR. Okay, the MR has already been conveniently given to you guys. So go and find that, and then afterwards, just go and substitute into your KSP expression, and you're pretty much done. Okay, so give that a try. Okay. Make sure you got you calculate the answer on the top right. Okay, then you're pretty much safe. And once you're done with that, okay, perhaps we can look at the next question also. You need a calculator. Alright. Your intermediate answers always 4 or 5 SF. The final answer, then you round off to 3. Okay, can you get the answer at the top right? Can now? Okay, then from there, we're just going to move on to the next page. Okay, the next question, right? There is a small little thing there, okay, that we need to take note of because y'all haven't learned yet. So let me just give you the formula, right, for what is required for this next question. But generally speaking, right after this, okay, the steps are pretty much the same. Okay, so guys, they tell you, right, one information here, the pH of FeOH2 is, what is it, 9.5. Okay, and right? pH means what? pH has a formula called negative log of the concentration of H+. You can go and try type in the calculator and all that. So that means, okay, I give you all this because you haven't learned yet. If you want to find the concentration of H+, right, you reverse the process. You take 10 to the power of negative pH. Okay, again, these are the formulas you eventually learn. Okay, so this is the two things you need to know first. Okay. If you want to find, again, because if there's H plus, right, there's OH minus also. If you want to find OH minus, you just need to take 10 to the power of minus 40 divided by the concentration of H plus. I place these three formulas here first. You're going to figure out how to do this question. Okay? I suggest you all just follow these three steps as per normal first. When the calculations begin, then you need to use these formulas. Okay? Pretty much, okay, you all don't actually need the first formula here. It's just to make things a bit easier. Okay, but that's just a similar formula. Okay, again, just go and do the three steps, same as before. Okay, numbers wise, okay, you just need to do a little bit of additional things. Okay, give it a try. Okay. You need a hard copy. If not, you can just pass me back. Okay, define your solubility and all that. Yeah, I know I don't write my state symbols here. You don't need to write state symbols when you perform calculations. Okay, the state symbols thing was just to ease you guys into the idea. Right? Okay, so by this point, right, you should get your S, this S, this is 2S. Since they want you to find the KSP, the third step is just to sub these values into your KSP expression, and same thing, you still will get 4S cubed. So this is the same as what we've done before. Okay, but now try to tie in, right, this value of 9.5 into your answer. Okay, so give you guys a bit of time to try that. Okay, any decrease here? Okay, so it's a bit challenging. Okay, it's a bit challenging. So let's go over this. All right. I know you guys haven't really learned the formulas yet. Okay, but let's not just toss in the formulas for no apparent reason. Okay, this first few parts here, okay, it's the same as before. Yeah, define my solubility and whatnot. I somehow need to find a value of S to find KSP. Correct, right? Okay, how do I find the solubility of the salt? The only information that they've given us is that the pH of this guy is 9.5. Now, I told you guys that pH, right, allows you to find the concentration of H plus just by using this formula. Okay, but we can also find the concentration of OH minus. Just to be very clear here, what am I interested in? H plus or OH minus? If you just take a look at your equation here, I'm only interested in OH minus, right? Obviously. There's no H plus in this question. So I only have OH minus right here, right? So basically, let's just do the necessary first. I'm just going to take 10 to the power of negative 9.5. That's to find the concentration of H plus. And then afterwards, I just sub it into this second formula, and that will give me the concentration of OH minus 10 to the power of negative 4.5. You can go type in the calculator and whatnot, I'll just stick it to this first. Can see that? Okay, so I have found the concentration of OH minus, and now I have another problem. That is that the solubility? Did they explicitly say? No. If you look at the previous question, they told you guys explicitly that the solubility is 4.47 whatever. But here they never use the word explicitly, the word solubility. So what's going on here? I need you all to highlight saturated solution. This is what most questions will do. I need you all to highlight the saturated solution. So guys, they are saying this. The pH of this FeOH2 is 9.5, and this is a saturated solution. Guys, what does this mean? It means that this OH minus concentration is the maximum amount that's inside that solution, correct? And guys, what does this value actually represent? This is the maximum concentration of OH minus ions. So this is essentially the solubility. Can see that? Okay, we already defined the idea. A solubility is not just some random concentration. It is the maximum amount of ions in that solution. So the question here has said that it's saturated, meaning that this concentration here corresponds to its solubility. You can start to see this connection here. So can you take a look? What is the concentration of OH minus here? It's represented with 2S. Can see that? So 2S is your concentration of OH minus at its maximum, which is this value that we have just calculated. So if 2S is this value, what can I now find? I can solve for what? Solve for S, right? S is just 10 to the power negative 4.5 divided by 2. And from here, I can just sub this into my KSP. Okay, so go give that a try. Can start to see what is going on over here. Okay, they will slowly start to introduce words that are not as direct, not as straightforward. Okay, you guys need to be able to pick that up. Okay, you can answer. Okay, you will just give it a try first. Okay. Any issues to clarify here? Okay. 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 Oh, it's not 9.5, it's 4.5. Because you needed to convert 9.5 is the concentration of H plus. But there's no H plus in this question. The question here only is OH minus. That's the time you need to find OH minus. So it's only 5. There's no H plus. Only OH. So we eventually learn what pH and OH minus have, what the connection are. So I know now that a bit blurred. Okay, but the idea is I'm only interested in OH minus. So that's why I expect you to just follow the equation. See, right? S to S. Your FeOH2, okay, remember this is bracket wrong. FeOH2 is a solid. Solid is a concentration. Square brackets represent. So this is just wrong. Okay, so it's basically 2S. Your concentration of OH minus is this value here that we just found. It's not the FeOH2. That guy's a solid. Okay. Right? Okay, you can proceed over the next question because the next page, right, is a similar type of question. You just follow the 3 steps and do one. Yeah, okay, so just give it a try also. Okay, just do question 1. Okay, not to worry too much about this question yet if you're feeling a bit confused, because when we do learn these formulas in a future topic, right, the connection is very simple. Okay, so not to worry about that yet. Okay, so just try the question on page 9. You should start to get into the flow of how this question is calculated already. Okay, so this time round, they want you guys to calculate solubility, but they give you KSP. The same thing, but they just swap the order. Okay, so same exact steps. Right. Good. Can nice. Which part of Greece are you going? Just Athens. Oh, so you're not going out of Greece. Okay. Oh, their economy collapse or some shit. Yeah. So you're going there. This scary, so. Yeah, I think I now remember. A lot of people actually went there last time also. I think it's very nice. Is it winter there now? Or summer? Oh, really? Not very cool. Okay, let's go last time. So it doesn't snow lah. Oh, shit, that's nice. Oh, damn. Okay. Okay, can you get answers? Okay, can. Alright, okay, there's another question, okay, but we're not going to waste time on that because it's pretty much the same thing. Okay, at some point this gets very repetitive. Okay, so this is just an easy question time. Okay, now I need you guys to turn over. We're gonna slowly progress. Okay, so start to add on more stuff. Look at page 11 now. Okay, this is where things start to get slightly more interesting. Okay, because the first part of today's lesson, we discussed KSP and solubility. These two are pretty much together. But now, right, we're going to introduce a new concept here called ionic product. Okay, IP for short lah. Okay, I'm going to use the word IP from now on. Okay, so IP, first of all, you can look at the definition and you'll realize it is the exact same as KSP. Let me just give you guys a few bits and pieces of information first. If the KSP of AgCl is Ag plus Cl minus, this is how we did it just now already, the IP of AgCl is also Ag plus Cl minus. In other words, the same shit. Then you'll be like, what the hell? Then why are we learning this? Okay, if it looks the same, then should it be the same thing? No, not exactly. There's a few slight differences. Okay, the number one thing, right, that it doesn't have when you look through the definition is that the IP, right, is not at a saturated solution. Just now we keep focusing on the idea, right, that KSP measures the maximum amount of ions. But IP doesn't have that restriction, right? Maximum, there's just one maximum only. But IP doesn't have this restriction here. So I want you guys to look at the differences between IP and KSP. There's a small table there, right? But just focus on the board here first. Okay, between IP and KSP, the number one most important thing is that KSP, right, only measures ions only at a saturated solution. Whereas for IP, if it's not at a saturated solution, what does that mean? It means that it's a lot more flexible, right? It doesn't just measure at one point in time, because we already said that saturated means maximum. And there's only such thing as one maximum. So for IP, right, it measures ions and both unsaturated, which means not at the maximum, and saturated solutions. So you can see it's a lot more liberal, a lot more flexible compared to KSP. I know looking at this, you're probably like, what? How can it be both unsaturated and saturated at the same time? Never mind. Okay, you all will see the idea soon enough. Okay, to be more specific here, KSP, how many values do you think you will have? It's only at a maximum point. So how many values of KSP will there be for one salt? Considering the temperature is the same. It'll be one. In other words, good, it is a fixed value. KSP is a fixed value that you cannot change. No matter how you change the concentration of the ions, it's not going to affect KSP. Whereas, guys, how about IP? Does it just take up one value? No, right? Okay, because it measures any amount of ions in a solution. So it can take up any value. So a lot more flexible here. We're going to go into more detail. Okay, so can see this so far first briefly. Okay, the next page is calculations, but we're not going to do this first. Okay, let's not disrupt the flow. Can we turn over to page 13? We're going to now see, right, how this works and what's the purpose of this. Okay, so on page 13, right, we're going to look at a very important application. We can actually compare IP and KSP together. Okay, so we have two values. We can hit these two values together, and it has one purpose. It is to predict precipitation of a salt. So when you compare both values, there's a metric. Sometimes the salt can precipitate, sometimes it doesn't. So this will help us to predict that situation. I'm going to write down the scenarios first, and I'm going to help you understand this a bit more. Okay, now the first scenario is when IP is less than KSP. When the value of IP is lower, you are not going to see any precipitate. Okay, and okay, I'll look at more detail. I'm just going to write this first. There's no precipitate. IP can be more than KSP, and there will be precipitate form. Finally, you can have IP just nice equal to KSP. And what this means is that you're going to see, okay, perhaps let's not write this down first. Okay, now, how do we visualize this? You all can't see anything yet. You have no idea what IP is. You can't really understand what KSP really is as well. But I want you to come back to this idea. KSP is a fixed value. So let me give you an analogy. imagine the KSP, right, is a water bottle. It's a 1 liter water bottle. Now, guys, when you wake up tomorrow, is your water bottle going to change in capacity? Is it going to shrink? Is it going to expand? No, right? The point I'm trying to drive at is that a water bottle is fixed, no matter what. Can you see that? On the other hand, I want you to imagine, since IP can take up any value, I want you guys to imagine the water level, right, inside this water bottle. Can the water level in the water bottle change? Definitely. Okay, some days you can have the 1 liter full. You can have 300 ml like my bottle currently, right? Okay, the point is our water level can take up any value. So you imagine this, if my KSP, my 1 liter water bottle, I put in only 700 ml water, which is less than 1 liter. Okay, is there going to be any overflow here? Is there going to be any spillage? No, right? Okay, it's just going to be contained in the bottle. On the other hand, guys, if I have a 1 liter water bottle and I try to pour in 1.5 liters of water, can you all tell me what happens here? What's going to happen? If I try to pour in 1.5 liters, right, into a small little 1 liter bottle, what's going to happen here? What's going to happen? You all need to know this, I'll vocalize it. So, you're going to have an overflow of how much? 500. Okay, guys, this overflow of this spillage of 500 is basically the precipitate. Because I want you to imagine this. Your water bottle, right, is like the solution. Anything that comes out of the solution is a solid already. Anything that contains within the water bottle is within the solution inside. That's why you do not see any precipitate. Can you see that first? Okay, any spillage comes out as precipitate, anything that's inside remains as ions, no precipitate is formed. Can you see that? The final scenario is this. If I have a 1 liter water bottle, and just nice, we have all done this before, you try to fill it up to the brim. Guys, what's going to happen here? If you fill in exactly 1 liters, what's going to happen eventually? Unavoidably, what's going to happen? If you try to fill in 1 liter water bottle, right, at the brim, there's going to be some water that will, what happen? What's going to happen over here? If you try to fill in exactly at the brim, then you carry the water bottle away, right? What's going to happen to that? Okay, there's going to be a bit of overflow, right? So what happens when IP is equal to KSP? When a little bit overflows out, that means you see a little bit of what? Precipitate. Okay, so I need you all to take note. When IP is just nice equal to KSP, you see the first trace of precipitate because you're going to see a little bit of spillage. This is where it begins to form precipitate. And then the more you add, the more water that you try to add into the brim, right, it's just going to flow out. That is the more precipitate starting to form. Can visualize this so far? I'm pitting two values together and comparing the three different scenarios. Okay, I'm going to end one more thing, guys. Can you all tell me now the second job for each scenario, is the solution saturated or unsaturated? Two things, very simple. Okay, you all tell me the first one, is the solution saturated or unsaturated? Okay, unsaturated because why? It has not hit the maximum. Can you see that? Okay, so the solution currently is unsaturated. Now next, guys, how about the second scenario, saturated or unsaturated? Okay, because it has at least hit the maximum, right? You have formed precipitate, so it is a saturated solution. Guys, how about the last one? Also saturated, right? In fact, it's just saturated only because you have just hit the maximum. Okay, so these ideas, right, of saturated or not, just picture the idea of maximum. Whether you have hit that capacity, whether you have hit the 1 liter capacity of your water bottle. Say again, anything that comes out, anything that spills out, it comes out as a precipitate. Anything that stays inside, that's contained inside, that is your solution, ions, no precipitate. You can see that so far. This idea here is very important. We'll carry on to the rest of this topic already. So far, so good? Okay. There's a box at the bottom of that page. Let's try to answer this. Okay. Now, they want us to, we can look at it from another way. You can look at this water bottle analogy, right? But we can also look at it from position of equilibrium, which we have covered before. So I need you all to try this. Okay. Explain in terms of position of equilibrium why precipitation occurs when IP is more than KSP. Now we're just going to explain from a concept that we have learned before. Okay. First of all, we'll write down the expression. Okay. PbCl2 is a sparingly soluble salt. Okay. You dissolve into its respective ions. what we're trying to explain is that IP is somehow more than KSP. And just for starters, right, I need you all to write down the IP expression of this PBCl2. Okay. Okay, why do you form precipitate when IP exceeds KSP? Let's look at it from a more legit standpoint now. Guys, when IP exceeds KSP, that means IP is high or low. Is IP high or low in order to exceed the KSP? It has to be high. Now guys, if the IP is higher, what does that mean about the concentration of ions? High or low or unaffected? First of all, does the concentration of ions affect KSP? Go back to the idea that we talked about just now. Does concentration of ions affect KSP? Yes or no? Come, give me a guess. What's KSP affected by? What's KSP affected by? Temperature only, right? So it's not affected by the concentration. Concentration does not affect KSP in this case, but guys, how about IP? Okay, IP, is it affected? Answer will be yes. Okay, so yes, when the concentration of ions are high, IP will be high. Likewise, if the concentration of ions are low, IP will be low. Okay, so IP is affected because you can take up any value. It's not just one fixed value. So it's actually affected by the concentration of ions. So when IP is high, it implies that the concentration of ions are very high as well, right? Guys, what does this mean? When the concentration of ions are higher, is it just going to stay high? Look at the equation here. What's going to happen? The moment this right-hand side is higher than the left-hand side, what will happen? Good. The position of equilibrium will now shift towards where? The left. Again, now guys, this is an equilibrium. When there's a disturbance in the equilibrium, you want to go back to normal. You want to reset back to normal. So if this goes high, it will not stay high. It will shift left, okay, to get this ions concentration back to normal. So guys, what happens when you shift left? What are you actually doing here? You're shifting left, so you're going to form more precipitate. Can see that? That's pretty much it for this part. Okay, so I need you all to take note of. Okay, when the concentration of ions are high, position of equilibrium shifts to the left. So you tell me this. We start off at the question first. The question told me about IP more than KSP. So when IP is more than KSP, okay, it means the concentration of ions are high. But it doesn't stay high. This is all about equilibrium. So thus, the position of equilibrium will unavoidably shift towards the left, and you form the PbCl2 precipitate. Can see that? So we have tied in different ideas, right, into this IP-KSP thing. I gave you guys an analogy just now, right, to really understand this a little bit better. By the end of the day, okay, it's all about position of equilibrium. Can we just do another scenario here? Okay, just to make sure you guys are understanding this. What happens when IP is less than KSP instead? Can we just look through this idea? When IP is less than KSP, what will happen conversely? When IP is less than KSP, that means the concentration of ions is what? High or low? Let's bring you all through this. When IP is less than KSP, the concentration of ions are very low. When concentration of ions are low, does it stay low and then just finish? What will happen? What will happen to the equilibrium? Concentration of ions are low, so the position of equilibrium will shift towards the right. Too low already, right? So I need to produce more. What's going to happen here? Are you going to form more precipitate? You are forming more ions. You are dissolving more precipitate. So that's why IP less than KSP, you don't form precipitate because it starts to actually dissolve. You can see the idea here. It's all about position of equilibrium. Okay? If there are no questions, okay, we're going to now start a little bit on the calculations. Okay? Once you finish your calculations, then we take a short break. Later we still have another segment to do. Okay? So far, this topic manageable? I think it's quite manageable so far. Later, there's only one challenging segment, but I'll bring you guys through it. Okay, can you all go back to page 12? Okay, before we look at page 14, it's pretty much the same shit. Okay, on page 12, I need you all to just look at question 1 and just calculate the IP. Okay, I already told you guys how to write the IP expression. So basically, just do that. Okay, see whether you can get the answer on the top right. It's not very tough. Okay, just read the question, calculate IP, and read. Okay, very quickly. Okay, page 12, question 1. Firstly, think about it first. Okay, you can try first. Okay, now I'll talk about why so weird. Okay, so that's just the IP expression. They give you the concentration. All you need to do is just sum the values. In the meantime, you can possibly screen the question, see if there's anything that stands out. Oh, there's no square there, right? Okay, which question is it? Yeah, you're on page 12. Yeah. Okay, we went back one page, right? Okay, so let's try this. Okay, so perhaps let's just go through this. If you try to sub in the concentrations given to you, you'll not get an answer on the top right. Why? Okay, so I want you to take out your highlighter and highlight equal volume. Okay, that's one thing that they purposely sneak in, right? And then no one can see. Okay, but take note, this keyword here is very important. Equal volume. What does that mean? Guys, they never specify the volume. Okay, but what they did say is that the volumes are the same. Okay, so imagine this, calcium 2 plus, they say the concentration is like, let's just say it's just 0.1. Okay, let's make it easier. Okay, then SO4 2 minus, they also get the same concentration, 0.1. But the issue is they are mixing them together. Now, they never say what volume it is, but let's just say it's 10 cm cube each. Guys, when you mix together, what's going to happen? What's going to happen to the volume? Mixing two solutions of equal volume will give you twice the total volume, right? So what does this mean? Can you all look back, right? Okay, what does this mean for the concentration of each ion? Does it stay the same? Okay, no, right? It doesn't stay the same because should it go higher or should it go lower? Should it become more concentrated or more diluted? When you mix things together. When the volume becomes larger, it should become more diluted, right? You can see that. Okay, but how do we calculate this? Guys, what is the formula for concentration even? Concentration is just number of moles divided by the volume, right? Guys, first question, the number of moles of calcium 2 plus before and after, is it going to be the same or different? Same. You're just mixing together, right? Whatever you put in is the same. So the number of moles will not change. Let's just use a tick to represent that. But guys, what happened to the volume here? The volume increases how many times? It is equal volumes. Increases 2 times. So guys, what will happen to the concentration? Half. Inversely proportional relationship. So in other words, guys, for each of these concentrations here, what I need you all to do is to divide both by 2, and then you multiply each of them together. Then you can get the final answer. You can start to see what's happening here. Okay, so it's a bit tricky, okay, because of the word equal volumes. You are going to double the concentration, double the volume, and as a result, half the concentration. Yeah, show you guys 2 different ways of looking at this. You want to look at it this way, go ahead. But I prefer this. Okay, it's a very simple inversely proportional relationship. With that said, with this part in mind, caring about the total volume, go and look at question 2. Okay, read through question 2 first. I'll give you guys a tip to calculate. Okay, don't calculate anything yet. Okay. Okay, first of all, can you just write down the IP expression? Just leave it there first. Okay, there's so many different ions there. Must be careful which one to use. You got BaNO3, then suddenly you got Na2SO4. Wow, what's happening over here? Okay, so what should be the IP expression? Okay, what should it be? It should just be Ba2 plus SO42 minus, correct? Okay, you all must be very careful. Your IP and KSP is all for sparingly soluble salts. We have learned solubility table in your secondary school before. Remember, nitrate and sodium are 100% soluble. So they'll never be part of any IP or KSP expression. Can see that first? Okay, now the next thing is this. Okay, you see they mentioned the volumes. If they specify volumes, you really need to account for that. Can? Okay, are the volumes equal? Did they add equal volumes together? Okay, then there's an issue, right? The volumes are not equal. Can we just divide by 2? Unfortunately, we can't. Correct? So I'm going to show you guys a very quick and easy way of calculating each concentration. So if you want to find the new concentration, right? I need you guys to take the O concentration, the initial concentration, and multiply by this thing called the dilution factor. Let me just write it at the side. The dilution factor is just to help you calculate how many times the concentration is getting diluted by. So the dilution factor is always take the volume and divide by the total volume. So in other words, I have to multiply by the volume over the total volume, and you can get the new concentration. Okay, guys, the O concentration of Ba2 plus is 2 times 10 to the power minus 3. Guys, okay, then what should we multiply it by? What's the volume of Ba2 plus that you throw inside? It's 0.1, right? What's the total volume? Okay, what's the total volume here? 8.4. Okay, so guys, can you see how has the concentration changed? This dilution factor is a ratio, right? The concentration is reduced by 4 times. Can you see that? Okay, 1/4. So with that, it allows you to find the new concentration of Ba2 plus. Repeat the same thing for sulfate. Okay, go give it a try. Okay, find the new concentration. And from there, later you all can sub it into the IP already. Okay? Okay, give it a try. You can see Japan won Spain for what a shit. Didn't expect that, sir. I thought they very good. Okay. All the possession, right? But they couldn't score, is it? I didn't watch the match, but I saw, wow, how bad Japan top of the group.
Japan won the excellent. But it's not like
Sorry, because I know they lost to Costa Rica, which is the bottom of the group. But they won Germany and Spain, and that was crazy.
maybe they have 7
With what?
17%.
How's that possible? It's just they got lucky with the goals. Wow, not bad. 17% possession still can score two.
Like Morocco top
Okay.
So Japan
They're gonna play Croatia, right? Wow, check on. Okay, but then that means their conversion higher. Possession to goal. Conversion is higher. Wow, interesting and a lot of upsets. Like that more exciting. It's not very predictable. Yeah. Okay, but anyways, again, we have your sulfate, right? Okay, so sulfate in this case was 4 times 10 to the power minus 3. Okay, the dilution factor is this. Okay, then you can dilute it by 3/4 times. Okay, you get these two concentrations, you sub it into your IP, you should get the answer on the top, right? 1.5 times 10 to the power minus 7. You get that? Sorry, 5 times 3, 15. 10 to the power minus 6. Okay? You have the answer on the top, right? So it should be that. Yeah. Any questions about? Okay, I want you guys to now flip over to page 14. It's the exact same calculation type. So go and give that a try also. I just need more, you all need to keep practicing. Okay, no choice. Okay, but if you look at the format of how they ask the question, you can already see they're asking for something a little bit extra. Okay, and that's what we have already learned just now. Okay, so just go and try these two questions yourself. Remember, you need to modify each concentration because the volumes are different. So when they mix together, you're going to get a different total volume. They're going to confirm get diluted. So remember to use the dilution factor. Okay. You okay? You look very tired. You okay? I look tired. Holiday should be the most energetic you ever be. I realize you all get more tired after exams and after that, after shook already. No choice lah. Cannot adjust or you just book up. Or just sleep or you watch the match. Yeah, no choice. Work out different. Once in 4 years is no choice.
I mean, I see.
Oh shit, that's the life. Oh, 2 o'clock. Wow, today's an early day. No choice. Wow. Okay, no choice. But last night's match, really need to watch. That was exciting. Why are you so tired nowadays? Tired tuition, but then go out, it's like, wow. Like, okay, already. No choice, cannot get lazy. If not, your brain start to get lazy, right? Wow, cannot, difficult. Then next year when you want to start studying again, damn difficult. I tried that before. When you stop studying for an extended period of time, you don't want to start ever again. And when reality hits you in the face, then you realize too late already. Wow, then the panic starts to set in. I experience too much of this coping right now. Yeah, too much copium already. Never mind. Okay, holidays can chill a bit, never mind. We'll see you guys. It is the last time we're going to see you guys for the month anyway. We're going to fly the next time. Shiok lah. Yeah, last lesson come out for the year. Okay, so anyways, okay, the first one, okay, any issues? Oh, you did the first one. Oh shit. Come on, I'm gonna try. Push on after these 2 questions, I give you all a break. Yeah, I think you all need a break. Pass game first.
I don't want you just bring it.
No, must try. I go through pointless. Hey, you. Come, faster. No, must try more. Change the dilution factor only. Come, I give you one answer. Come, this one here. What's the dilution factor? Cannot lazy. Last lesson already. You have Japan in a few days. This one must have more motivation. Bro, even Greece. But must settle some stuff first. Then holiday you can relax. Huh? Your flight's at 3. Okay, well, that means your body clock is used to be already. Later go back after this, go take a nap. Yeah, take a nap, then tonight you can go on the plane. Then watch World Cup in the airport. Go have fun. Yeah, fun, right? Now do work first. Do work first, come on. Legit. I also damn looking forward to my trip because I like this. I just don't want to do this shit. Yeah, because that's why I finals was like just push through this nonsense. Finish already, right? Can relax a bit. Yeah, finish already on Monday. It was a fucking hellhole. It's like 4 days in a row of exams. So damn shit. Yeah, keep going school, then I was like having flu, then just doing the paper. It's just a hell of a time. Yeah, but then finish already, then I'm like, oh, finally, now the next thing to look forward to is the trip. But before the trip, I need to settle all the classes first. Okay, make sure that you all also settle all this, also the next year we don't so stress. Yeah. Yeah, and then they suddenly say, wow, must complete this, if not next year we don't have time to complete. So that's why we're rushing through this. Okay, we're not rushing through this, but then we skip through arrange already. That one you all to go and self-directed learning, like, oh, come back, must do yourself. Yeah, no choice, I need to enforce something already. Yeah, okay, but anyways, this first one, what's the dilation factor? Come. What's the volume of PB2 plus? What's the volume of PB2 plus? What's the volume of PB2 plus? Six. Oh, after the calculation, right? Okay, so the volume is 0.1, the total volume here is 0.5. Just take note that you need to add both together. So you have diluted it 5 times less. Yeah, diluted lah. Okay, so here will be 6 times 10 to the power minus 4, right? Okay, then from there, do the same thing for SO42 minus. What's the volume of SO42 minus? You see, it's just a matter of fraction, right? Okay, this one will just be the remaining fraction, 0.4 over 0.5. You see that? Yeah, it's just a fraction, okay, upon the total amount or total volume that you have. Okay, then from here, this is a much easier calculation, 10 to the power minus 4. Okay, once you've gotten these two concentrations, what do you need to do? Sub into what? Okay, very simply, sub into your IP, right? Your IP in this case is 2.4 times 10 to the power minus 7, right? But that's not what the question is asking now. They don't want you to calculate the IP. They just ask you guys, will a precipitate form? That's it. I feel like I calculated something wrong here. Yeah, 10 to the power minus 6, sorry. This 3. Correct. Okay, correct. So, yeah, okay. So, because of that, right? How are we supposed to answer the question now? We have the IP, and we must compare this against the what? To compare precipitation, to predict precipitation. What should we do? Okay, compare it with the value of KSP. So is this larger or smaller? Okay, yeah, they will have to give you the value of KSP. Okay, KSP in this case is 1.6 times 10 to the power minus 8 is larger. So express your answer like that and quote the values. And since IP is more than KSP, just give me a short little statement here. A precipitate will form. Okay, so that's for number 1. Can see that? Okay. Right, it's literally just comparing IP and KSP. Your only job here is to calculate IP. Because as I said, IP can take up any value. KSP, they will give you. Then you just compare. Guys, how about the second one here? This one, the working is shorter. Can we just sub in the two concentrations there? We have to account for the volume first, right? Okay, what do you notice about the volumes? What should we do to the concentration? Yes, okay, it's equal volumes. Okay, equal volumes even faster. Okay, take your SR2 plus 5 times 10 to the power minus 4 divided by 2, and you repeat the same thing for sulfate. Okay, sulfate in this case, 2 times 10 to the power minus 3 divided by 2, and then you multiply both together. Okay, this SRSO4, whatever this is. Okay, can? Calculate already, your answer here should be 2.5 times 10 to the power minus 7. Okay, then what should we do next? Okay, is it larger or smaller or whatever? Okay, now it is smaller than the KSP. Go and quote the KSP 8.1 times 10 to the power minus 7. So guys, what's the statement here? Will a precipitate form? Answer here is just no, no. Okay, no precipitate form, because this is the opposite of what we saw just now. You see that? Okay, express answer like this. Okay, this just to calculate IP and KSP. Thanks so far. So up until this point, okay, this topic here, very manageable. We take a break first. Later, we need to go over one more segment. Can? Sorry, you're friendly. Yeah, no worries. Record anyway. Yeah, we take a short break first. Later, we just go through this one more segment. Then we're done for today. Yeah, okay. So we still have a bit of time now, right? Okay, you are. Why you suddenly your head down like one time? No, cannot. Come. In another 10 more minutes, you're free, and then you can go overseas already. Think about the good side. Come on, guys. Let's look at page 15 now. Okay, so very quickly, I'm gonna touch on this one question. It's a one idea. This question here, okay, we have talked about IP and KSP. Now we're gonna look at probably, right, possibly the most challenging part of this topic. We're gonna call this selective precipitation. Now, don't worry, I'm gonna ease you guys into this idea here. Okay, based on the name itself, I'm sure you can guess. We're gonna precipitate salts selectively. Okay, like I'm gonna choose which solid to precipitate. Okay, and that's possible because of a few things. Okay, so I'm gonna give you guys a scenario first. Okay, follow me on this. I have a container, and in this container, I have two ions. It's contaminated lah, basically, with Pb2 plus and Ag plus. Now, of course, no scientist, right, likes contaminated shit. Okay, because you can't do anything, right? You want your stuff to be pure and clean. So then, because this is contaminated, right? Okay, then someone walk up to you and say, can you please go and purify this? Can you please go and separate the ions? Now, guys, what will you do? Are you going to tell me, right? You're going to take a piece of filter paper and filter funnel and try to separate this? Guys, is that possible? Can you take a filter paper and filter funnel and then just pour this inside and then it will separate itself? Can. No, right? Why cannot? Okay. Let's talk about this. Why cannot? What's a very simple reason why you cannot use a filter paper and a filter funnel? Do you have any solids? No, right? Okay. So the idea is this: there are no solids. They are both ions. You can't just use a filter paper yet. So why not? Let's precipitate them so that we can then use a filter paper to remove. Can see that? Okay, now the second question that I need to ask you all is this. Okay, I need you all to think about it. What I'm gonna do now is I'm gonna add in Cl minus. Cl minus will cause some of these guys to precipitate. But can you look, imagine the whole purpose of this experiment. What is the objective of this experiment? Of course, my purpose is to remove and separate both ions. But guys, how many salts do I want to precipitate? Do I want to precipitate both as solids? Think about it. Should I precipitate both ions as solids? Think about it. Cannot. Is that viable? Precipitating both as solids. Guys, if you precipitate both as solids, can you then filter them out? No one, right? Imagine this, it's a bunch of goo at the top, bunch of shit. It's just a mixture, that disgusting mixture of AgCl and Cl2. You can't separate that. So guys, how many solids do you want to precipitate? How many should you only be precipitating? One. You only precipitate one as a solid, and the other guy remains as a ion. So I want you all to write this objective down. The objective is to precipitate only one ion as a solid, whereas the other ion remains as an ion, remains in the solution. Guys, when this is done perfectly, right, what's going to happen is that I'm going to have a bunch of solid on top, and then the other ion remains as a solution. Then I can just simply take a filter paper to filter it away. Does that make any sense? Okay, so guys, you have to bear this in mind because we're going to have to repeat this as we go along. The next question is, why is this possible? How am I able, right, to just precipitate one as a solid? I thought when I add Cl minus, both will just come out as solid instantly. Guys, in the first place, these solids, PbCl2 and AgCl, do you think they have the same solubility? Are they exactly the same solubility? No, right? Different salts have different solubilities. Can see that? And because they have different solubilities, some will be more soluble, some will be less soluble. We can take advantage of this difference and precipitate them at different points in time. Agree with the idea? So what we're going to do, this is the answer for the box over there. Why are we able to do this? Is because different solids have different solubilities. And because of that, okay, they have different KSPs as well. Different solubility, different KSP, hence they can form precipitate separately. And because of this idea here, we can take advantage of this very fact and perform this selective precipitation experiment. This is pretty much it. This is the idea behind this experiment. Now we're going to proceed to the calculations. That's all I'm going to do here. Okay, so far. Turn over to the next page, page 16, sorry. We're going to answer these three parts, and that's pretty much the entirety of this segment here. Okay, we're going to go straight into the calculations, but guys, before that, I want you to write down, I'm going to have three things to figure out. The first thing to figure out is which guy precipitates first. Who precipitates first? Is it AgCl or is it PbCl2? We have to figure out who comes out first. Because the guy who comes out is the only guy that gets precipitated. The other one cannot get precipitated at all. The second thing to figure out is where is the maximum separation? Where is the point at which you can separate the maximum amount before the other guy starts to precipitate out? There has to be a maximum to stop. There has to be a point at which you stop the experiment. Finally, guys, how much is left? Guys, when you undergo separation, right, ideally you want 100% to be separated out, correct? But in real life, there's no such thing as 100%. It's impossible to get a perfect experiment. So no matter how much you separate them out, right, there's gonna be some leftovers. And our job here is to also figure out who will be the leftovers. So to answer these three questions, we're gonna have to look at some metrics. We're gonna look at it slowly. Okay? Guys, let's look at the first question. Part A will help us answer the first question here. It's the same scenario. They gave us the KSP of these two salts. Here, guys, can you look at the question here? What is the minimum concentration of Cl minus that you must add over here for each salt to be precipitated? Guys, how many answers are you going to get here? How many answers are you expected to calculate in this part A? How many answers? Okay, what's the minimum concentration of Cl minus for each salt? So there are two salts, right? So you're gonna have to calculate this 2 times. You can see that. Now, guys, can you highlight the word minimum? The word minimum there is very important. Because when you add stuff, when you add Cl minus, there has to be a starting point at which you begin precipitating. So what does minimum mean? Okay, the word minimum here means what is the minimum condition to precipitate? Very good. The minimum condition to start precipitation is when IP is equal to KSP of each salt. So I'm going to go over with you guys one of the salts. And then afterwards, you'll try the same thing for the other salt. Okay, let me copy that here again. Okay, never mind. I'll just copy it here. Okay, so let's first do AgCl. So you want the IP to be equal to the KSP of AgCl, right? Okay, so we'll write down the IP expression. AgCl is not difficult. Okay, just write Ag plus, Cl minus. KSP they also gave us. KSP they will give you one. Okay, not to worry. Okay, 1.8 times 10 to the power minus 10. You can see that. Okay, guys, they want us to find the minimum concentration of Cl minus. If I have the KSP, that means I must also have Ag plus, right? Did they give me Ag plus? Did they give me the question? Come scan through. I want to calculate the minimum concentration of Cl minus to precipitate AgCl. I need you to write down this entire thing. Okay, don't just write that Cl minus. How do I find Cl minus? What should I do, guys? I have Ag plus concentration, right? They gave us. So all you need to do here, take the KSP, then just divide. Shift this to the other side, 0.01. So the answer here, 1.8 times 10 to the power minus 8. This is the minimum concentration in order to precipitate AgCl. Guys, is this number big or small? Look at it objectively. Is this big or small? It's freaking small, right? So is it very easy or very difficult to precipitate AgCl? Easy as hell, right? Okay, you add a little bit only, suddenly the precipitate starts coming out because this is the minimum required. If I add any less than this, then what will happen? Will anything happen if I add anything less than this? No lah. You all can understand the idea of minimum, right? Okay, any more than this, you're gonna continue precipitating, but this is the minimum required. So guys, can you all repeat the same thing, but for PbCl2. Again, IP now equal to the KSP of PbCl2. Write down the expression and whatnot. Okay, give it a quick calculation. Okay, let's try that. Okay, there will be space on the next page. So the next few parts, right, after this part, I'll do on the next page. I give you all space for that. Right now, the IP equals to PB2 plus. Be careful, there's a CL minus square over here, right? Okay, right, the same statement, minimum concentration of CL minus to precipitate PbCl2. Okay, they give us as 0.02. Okay, don't forget the square root, right? Because of the square there. So guys, you have two answers here, and this will help us for the next part. Okay, we interpret the values objectively, guys. Which one easier to precipitate? Just by the two values here. Which one way easier? Yeah, okay, because why? The minimum condition is much easier, right? Much lower. Okay, so very simply, guys, can we answer the second question? Using your answers in part A, which sort comes out first? You add slowly. You add CL minus slowly. Which one comes out first? Look at the two answers that part A. Okay, guys, which one comes out first? Okay, this is the minimum required for AgCl. Very easy. But to precipitate PbCl2, you really need to add a lot more. You see the difference? 10 to the power minus 8 and minus 2. That's about 1 million times the difference. So guys, which one will come out first? When you add slowly. You're adding this progressively. So it starts from small concentration and keep adding more and more. So who comes out first? AgCl, because AgCl has the lower minimum concentration, right? Yeah, that's pretty much the answer to this question. Our job here is to identify who precipitates first. And the guy who precipitates first is AgCl, correct? Well, the second question, guys, will PbCl2 precipitate? Look at the objective of your experiment. Is it meant to precipitate? Are you supposed to precipitate PbCl2? No. The one ion that precipitates out as a solid here will be Ag+. You cannot precipitate PbCl2. Can see that? Because if PbCl2 come out as solid also, you're going to have two solids, and that's a disaster. You cannot separate them. Understand? Okay, so guys, let's take a look at the explanation for this. For part B, I want you all to write that AgCl precipitates first, but go and justify. I know the question never asked, but I'm going to write down also. That's because the minimum concentration of Cl minus to precipitate AgCl is very, very clearly lower than the minimum concentration to precipitate PbCl2. That's why AgCl comes out first. And in fact, he is the only one that comes out first. Okay, go and write a note to yourself. Only AgCl will precipitate. In the meantime, Pb2 plus must remain as, it's just a note to yourself, not part of the explanation. It must remain as an ion in the solution. Then it fits the objective of your experiment. So in other words, guys, coming to our three goals that we are trying to fulfill, the guy that precipitates first, to determine this, is always the one with the lower minimum concentration. And the keyword here being minimum. Okay, go answer these three questions as well. Okay? So for part A and part B, we answered the first point. Then for part C, we can answer pretty much the second and third points. Any questions so far? No? Guys, flip over to the next page. Okay, there's a lot of space there. Okay, we very quickly finish this up. Okay, if not, it's very, very weird place to stop. Okay. Anyways, can you all look at part C now? Okay, for part C, right, turn over to the next page. We're going to draw in a diagram out there. Help us facilitate this. Okay, they ask us how can Ag plus be separated? They want a procedure. But more important, can you all look at the next part and highlight that? Find the percentage of Ag plus left in the solution. Highlight left. Guys, I'm trying to precipitate Ag plus as AgCl, correct? Okay, follow me through this. Ag plus, what will happen to its concentration as you add more and more Cl minus? Does it go up or go down? I repeat. If I add Cl minus, will Ag plus increase or decrease in concentration as I keep adding? What will happen? Increase, sure. Okay, Ag plus is sitting in the solution, right? I'm trying to precipitate out as a solid. So as I add more and more solids start to come out, that means my concentration must start to drop. You can see that? Ideally, it must drop to what? In a perfect world, it must drop to 0, right? So you can precipitate all the Ag plus 100%. But as I mentioned just now, there's no such thing as maximum. There's no such thing as 100%. So in other words, our job here is to find out how much is left over, which is what this question is about. Can see that? And in order to find out how much is left, we need to actually answer this second point over here. Where is the maximum point of separation? So come, I want you guys to draw in this diagram over here with me. Okay. Okay, let me draw here. Move space. Okay, let's draw in this diagram together. Okay, try to leave a bit of space on the left and on the right. Okay, because we need to write both ends up. Okay, let's draw an arrow going upwards. What this arrow represents, I want you all to write down stuff on the right side first. Leave space for the left for later. I want you all to follow me through this. Later, you all can copy at the same time. At the very bottom, my Cl minus is 0. I'm going to track how much Cl minus I throw inside the cylinder. It's just going to increase because I'm just going to add more and more, right? But I want you guys to take note of two very important points. And these 2 points are basically this. That's why I never erase this. These 2 are very important points for the concentration of Cl minus. They are like milestones, you can see that. Okay, which one comes first? Which one should I plot first? Okay, there are 2 points, right? The lower one is for AgCl or PbCl. Come plot together with me. Okay, guys, the lower one is for AgCl or PbCl. Cl minus just increase also low to high. Okay, based on the values, AgCl comes out first, right? So as you add more and more Cl minus, this is the minimum concentration of Cl minus to precipitate AgCl. Okay, write the value inside as well since we already calculated. And what's the second milestone? The one that's way higher. That's for PbCl2, right? Look at the value. So big, right? Okay, so this is the minimum concentration of Cl minus to precipitate PbCl2. Then write out the value as well. You can clearly see there's a huge gap because 10 to the power minus 8 and minus 2 it's like 1 million times the difference. Super big gap. Okay, these are the 2 milestones you need to take note of. And guys, just based on this, I'm going to ask you one question. Where did the experiment begin? Did it begin at 0? Remember, the objective of this experiment is to precipitate one salt. Where did this begin? Good. It began here. Not here, guys. When you add, okay, let's say my Cl minus I add until here. Will anything happen? Has anything begun? No, I haven't even precipitated shit. So nothing has begun here. But it begins here. This, I want you all to write down. This is the start. Can you see that? Next, where does it end? It starts here, sure. But guys, do you stop here? Do you add 1.8 times 10 to the power minus 8 and be like, okay, I'm happy, very good separation, settle, finish, correct? Okay, if you add like that a bit, you only precipitate a bit, right? Can you precipitate more? Can, obviously. So what do? To precipitate more, you add more Cl minus, right? Just add forever lah. Why not? I add as much as possible so that I don't have any leftovers. Then I don't even need to answer the third question. Just continue lah. But actually, there's a place we need to stop. There's a maximum that we can go. We cannot go beyond this point. Which point is it? Exactly, guys. Why can't we go beyond this point? Exactly. If you go beyond this point, you're going to end up having 2 solids. And we already said just now, that's bad. You cannot have 2 solids. So can you see what we're doing here? This is the end point. I need you all to really identify this. This is the point at which there's maximum separation. The maximum separation is at the end point. And the end point is at the higher minimum concentration. Can see the difference here. The guy who precipitates first is the lower minimum concentration. Where you must stop is at the higher minimum concentration. Just these two values. That's why I want to erase these two values. Okay, answer that second question also. Can see that? And guys, that's why I asked you to have space on the left, because on the left hand side, I'm going to track one thing. Guys, at the starting point, my Ag plus concentration, what was it? Did they give me the initial Ag plus concentration? They were give. Okay, did they give us in the question? Before you precipitate anything, is the initial concentration, right? Just 0.01. So go and track that value now. So right hand side, I track Cl minus, left hand side, I track Ag plus. Guys, this is 0.01, right? At the end, again, ideally, what do I have? How much do I have left? Ideally, I should left with 0, right? Again, it's just going to be a very small number. This is what I'm aiming to calculate now. Can see that? How do I calculate this shit? The working is only one step. I'm going to show you the working first. Then the logic behind it, I can explain. Okay, guys, if I want to find the concentration of Ag plus left at this point, focus on endpoint. I also have the concentration of Cl minus at the endpoint, right? If I have Ag plus, and if I have Cl minus, and I want to find Ag plus, guys, which expression should I use? Should I use the AgCl or the PbCl2 expression? Which one allows me to calculate this value? Obviously, AgCl, can see that. It's actually very simple. That's why I want you to draw this diagram. If you don't draw this diagram, you do not know what value to use. Just Cl. Yeah, okay, AgCl. I got Ag plus Cl minus. So what's going to happen here is this. Okay, I calculate here. Let's see. To find the concentration of Ag plus left, the IP must be equal to Ksp of AgCl. Again, now guys, why I choose AgCl is because I got these two values. So, to find the concentration of Ag plus left, I take the Ksp of AgCl divided by the concentration of Cl minus at this same exact point, which is why I calculated 2.83 times 10 to the power minus 2. I'll calculate the answer for you guys. Something like this. Can see that? It's a one-step process. One-step calculation. Some of you guys may have a few questions. I'll come to that. But in short, guys, this is all you need to do. I want to find Ag plus left. I lay it out very clearly with my diagram. At this same point, I have Cl minus. Just take AgCl. Let's just divide. Simple as that. Don't take PbCl2 because I don't give a shit about Pb2 plus. Okay, that. Guys, so if you go and edit your diagram, I have 6.36 times 10 to the power minus 9 remaining. Based on your intuition, guys, do you think this was a successful operation? You started with this, you ended with this. Was this successful? Do you think? Again, ideally, ideally, this one you all need to be how much? As close to 0 as possible, right? So was this a successful operation? Have you pressed? It was pretty good, right? Because it's very close to 0, honestly. You all must understand this is a very small number. It's in the billions. And guys, the difference is the what? That's another question I'm going to ask you. The difference between this and this is what? Where did everything go up? Where did everything disappear to? How come so little left? Guys, then perhaps don't know this to yourself. It's not calculated in this question here. But the difference between the start and the end is just whatever that precipitated out. Okay, whatever AgCl that precipitated out. That's it. This one may be asked in an advanced question, but for now, let's not deal with that. But get the logic first, get the intuition behind this first. Yeah, of course, I know AgCl is a solid. This is in concentration. So there's a bit of conversion you still need to do. But get the understanding first, carry. Hey guys, anyone has any questions regarding this working here and why I use this? Anyone have any questions regarding this? Or any questions regarding anything else? If you want to clarify, please clarify this now. Can you repeat one more time also? Okay, because the objective for this experiment is only for one guy to become solid, the other guy remain as ion. If one guy solid, one guy ion, I can just filter them out perfectly, correct? So if I end up adding more than this, I go past this endpoint, I'm gonna end up with what? 2 solids. 2 solids, bad. That's not what I want. I cannot filter that shit out. Right? You see that? Okay, so I'm gonna stop here. Again, by right, I'm supposed to stop before this, I can see that. You cannot stop exactly at this point. But in chemistry, we don't deal with inequalities like in math. So that's why we just assume it's exactly at this point. So this is the whole entire selective precipitation question, 3 parts. They can only ask about these 3 things most of the time. Of course, there's some additional stuff that you can ask about this, but that one is additional already. Okay. If there are no questions, that's pretty much it for this part. Of course, you all do this for the first time. You're not going to understand this 100%. That's why in the next lesson, right, we will have to do questions regarding this. Okay, and I'm aware both of you guys will be overseas by then. Okay, so there will be a solubility second part lesson, right, recorded, and you guys need to watch that also. Okay, so for the recording people watching this as well, okay, you all need to do Erin's 3 lessons to look through that topic and solubility this second part. The lesson has already been recorded. Just need to watch it, do the tutorial along with the lesson. Just follow the lesson plan. Okay, Ken? I know it's a little bit rushed, okay, but we know you guys need to follow the syllabus for next year. Okay, if you all need help, of course, I can always see you guys. Okay.